Okay, what we did last time, CDF, right? So CDF, sorry, CDF. What is the meaning of that? The word?
Well, another property.
No, the name. So this is short for. That is the cumulative distribution function, right? And what is that? So what is f of x? Right? That's the definition. So we have, again, we have this probability space R, the Borel sigma algebra of R and P, right? So this P is this P, the probability measure. And now, since we don't want to use P, we are going to use F of X, or the CDF of distribution. We know that there are two different, okay, we know that we have, if we have probability distributions, we have discrete and absolutely continuous, right? And we have singular, but we are not going to study singular right now, just discrete and absolutely continuous. And we started with the discrete probability distributions, right? We already know all of this, but let me remind you. So the first case, so when we have the discrete case, the first distribution that we know is the Bernoulli distribution with parameter P, right? In this case, if we have some, for the set in which we work, X is just 0 and 1, right? So we get 1 with probability P and 0 with probability 1 minus P. Yes, and that's it. And so the CDF in this case looks like this. So if we have here 0 and we have 1, and this is the CDF, right? So we know that for every x less or equal than 0, this is 0, right? But here, between 0 and 1, we have 1 minus P. Yes, this is closed, here is open, and here is open, and here we have 1, and like that. Okay, so this is the CDF for the Bernoulli distribution. Good. Now, what's the next distribution we know? The binomial distribution, right? The binomial distribution with parameters NP. In this case, we know that for, so X, so if here we had 0 and 1, then here we had what? What do we have? How many options? How many? No, n options, right? 0, 1, n. Okay, actually from 1, sorry, from 1. Okay. So, and in this case, the probability of x, right? So x is just any element from capital X. So 1, 2, or n, or and choose x, right? Yes. So this is what? This is the probability mass function, right? So we know that this is a probability mass function, PMF, right? Or we call the discrete density, but in English it's often to call it PMF. Okay, good. And in this case, what CDF we have? What CDF? Well, the CDF here is difficult to draw, so let's not do it. Let's move to the next one. The uniform distribution, uniform discrete distribution. Okay, so in this case we have, for example, when we draw a die, so we have 6 options and the probability of getting each number is the same. Okay, so for example, X is just some finite set. I don't know, for example, when we draw a die, right? So 1, 2, 6, for example, right? And for each of these elements, we know that the probability is just 1 over the total number of elements that we have, right? And the CDF for this case looks like this. So let me draw here. We have 0, we have 1, 2, 3, 4, 5, and 6, something like that. Okay. So before 0, actually, before 1, we got 0, right? Because the probability that we obtain, for example, 5, or the probability that we obtain any number less than 1 is 0, because the less number that we have is 1. So this is like this. Right, so like this. And then here, we can say that this is just P, right? And then we can go up, or here we have P. And then again like that. And then again P. So here we have 2P. And like that, right? This is for 4, for 5, and 1, 2, 3. Less or equal 5. Less or equal like this, right? So and here we have P, 2P, 3P, and so on. So the height of every step is the same, P. Okay, so here we had 1 minus P, and here, well, 1 minus P, right? This is the height. Here we have every time we have P here, and we have P here, and so on, right? Okay, and the length in this case is the same, but this can change, because here we have 1, 2, 3, 4, 5, and 6, but maybe we have minus 99 and I don't know, 10, right? So of course the length of this is going to change. All right, so this is the uniform discrete distribution. What else do we have? We still have the Poisson distribution, right? Number 4 is the Poisson distribution with some parameter lambda. And in this case, we know that X, so all the possible values for this random variable is just all the positive integers. And for any integer, we know that the probability of X is what? So what's the PMF of the Poisson? right? So this is lambda. So here we have x factorial to the power of x, and e to the minus lambda, right? E to the minus lambda. Yeah, like that. I think so. Well, you can check that. I don't remember everything by heart. So this is the Poisson distribution, right? Okay, perfect. And that's it. So this is all that we need to know for discrete probability distribution. And now we start with something else. We need to start absolutely continuous probability distribution. Okay. So what do we have here? In this case, what? How to say it? Look, in this case, there exists something called the probability density function. And that's because, just a second, yeah, so if there exists some function p, right? This function is from the set of the real numbers, yes, to the set of the positive real numbers. So if there exists such a function, that the CDF is equal to the integral from minus infinite to x of this function, then this distribution is called absolutely continuous. So if there exists such function p, then this distribution is called absolutely continuous. All right, so we have some measure p, right? Measure p. From here we say that we have some CDF, right? CDF is defined for every measure, for every p, for every possible p. P is from here, so don't get confused with this. So this p, right? This p, the probability measure. So for every p, we have a CDF. Okay, a unique CDF, and the CDF is defined for absolutely every possible distribution, for every random variable. Okay, but there's some specific kind of random variables or distributions, just distributions, for which we can define this function p. So this function exists only in some cases. And if this function exists, then we call this an absolutely continuous random variable or an absolutely continuous probability distribution, and this is called the probability density function. Okay, or the PDF. So it means that if we talk about absolutely continuous probability distributions, we talk about the PDF of this distribution, right? We are not going to talk about the CDF in this case because it's much better to use the PDF, the probability density function. Okay, so what about this function? What do we have for this function? So let me say, first of all, so the properties of the PDF. Don't worry, I will give you some examples a bit later. Okay, so properties of the PDF. The first one is that if the CDF, if f is differentiable, right? So if the derivative of f is defined in every point, in every real number, then from here, we can see that the derivative of this, or the derivative of an integral, is just the function that we have inside, right? Then the derivative of f gives us p. So this is the way of finding p. If we know f, we can find p. Only if f is differentiable, right? If it's not, then this is not possible. Okay, so don't forget about this condition. So this is the first property. The second property is that for every Borel set, it holds that the probability of B is the integral over B of the density. So how to explain this? I know that it can be confusing just talking about Borel set and so on. So let's talk about something else. What about, instead of B, we can take just the open interval AB, right? And we know that, and then it means that if the PDF is defined, then the probability of this open interval, right? And later we will say the probability that the random variable xi belongs to A and B is just the integral from A to B of the density, right? And in this way, we are going to find probabilities. If we know the PDF, we can easily find the probability. Okay, good. This B? B means overall B. B in this case will be from A to B. B is not a number. B is a set, right? So B is a set from the Borel sigma algebra. So an open interval or a half space and so on. Good. What else do we have? What else do we need? Let me see. I don't remember what other properties. We need, just a sec. So is everything clear by now? Sure? Yeah? Okay, great. Yeah. Yeah, exactly. Okay, let me see what else do we need to show from this. Yeah, so and finally, the other property that we need, and you need to tell me. So what is what is this equal to? The integral from minus infinite to plus infinite of the PDF. So look at this. So don't forget that this, okay, look, this, yes, is the probability that this random variable is between minus infinity plus infinity. What is that?
Probably this.
What is the probability that a real number is between minus infinity plus infinity? Yeah, so 1, right? So this is 1. Right? So look, I just haven't talked about random variables, but this is the probability that the random variable xi, I'm just going to talk about random variables a bit later, belongs to A and B. Something like this. So what is the probability that a random variable belongs to minus infinity to plus infinity? Of course, 1. So it should be somewhere. So this is 1. Okay, and this is very important because if, for example, we have that, you will have that homework. If you have that the density is some constant by some numbers, by some function, and you need to know what is the value of this constant. Of course, you just have to say that the integral over all the real numbers is 1, and so you can find the value of the constant, right? So this is very important. Okay, good. Now, what do we need to do next? I think, no, yeah, some examples, all right? So now we have two functions, right? Again, we have the CDF and we have the PDF. But the CDF is defined for every distribution. The PDF is defined only for absolutely continuous distributions. So this is defined for every distribution, right? And this is defined only for absolutely continuous distributions. All right. So if, for example, I ask you, could you please find the PDF of the binomial distribution? It doesn't make sense, right? So you can look for that, but you won't find it. That's actually a good question for the exam. I will remember. Yes, of course. So for every possible distribution. Now, what examples do we have? We have first, so examples. And by example, I mean the most famous absolutely continuous distributions. So the first one is that continuous, not continuous, sorry, but uniform. The uniform distribution. So look, here we had the uniform distribution for a discrete, in the discrete case, and here we have the uniform distribution in the continuous case. So what do we have here? We have here, we have that for the probability that we have each of these points is equal, right? The probability that we have this one is equal to the probability that we have this one, and so on. Now, in this case, we have some interval, for example, from A to B, and we say that the probability that we get for example, this interval is proportional to the length of A. So the probability, so we randomly pick a point from here, right? So a point from A to B, and we say, what's the probability that this point is in A? Then what we have to do is like A over B minus A, right? So the length of A over B minus A. Okay, so this is the geometric distribution that we already know, right? So what I'm trying to say is that the probability of getting a set is proportional to the length of this set. So right, if we have B like this, then the measure, the probability of B is going to be bigger than the probability of A. So that's the deal, okay? So look, so for every Borel set, we have that, right, such that the measure of this Borel set is finite, right? This means that it's finite, so it's not infinite, just like that, okay? We have that the probability of x, it's weird how here, yeah. So this is 1 over the measure of b and the indicator function that x belongs to b. So this is the PDF. Yeah, so this is the indicator function. The indicator function. So the PDF of every point x, right, is equal to, so if x belongs to b, it's just 1 over the probability of b. Measure, I mean here probability, right? So this is probability. So how big b is, right? Don't forget that this mu means p, okay? Yeah, so for example, let's change this b. So let's say that b is again the closed interval from a to b, right? So it means that for every point that belongs to from a to b, the PDF is going to be what? 1 over b minus a, right? The measure, the probability of b in this case is b minus a. And if x doesn't belong to a and b, to the interval from a, then this is just 0. So why do we need this? Look, let's draw this function. This is a, this is b, right? Of the real numbers here. And we want to draw the PDF. So what is that? If x doesn't belong to this interval, then that's 0. So we have that this is 0 here and 0 here. And if x belongs to this interval, this is this number. So somewhere here, we have 1 over b minus a, right? And then here we have that. This is the PDF of the uniform distribution. Why? Huh? No.
So PDF can get this function.
Yes, it has to be.
Oh, so it's also continuous on the right. So none of those.
No, it's different. Don't confuse it, right? So CDF and PDF are absolutely different things, right? So all the properties that we prove were for the CDF, because the CDF is more important, more general than the PDF. Okay, so the properties of the PDF are just, the main one is that the integral from minus infinity to plus infinity should be 1, right? So what is the integral of this function from minus infinity to plus infinity? So it should be 1. Why? No, I mean, look at this function. What is the integral of a function? No. Again, look at the function. It's the area, right? This area. This area. What is this area here? So we have here, we have b minus a times the height is 1 over b minus a. So this is 1, right? So the integral of this function is 1, right? So now, what is the probability what is the probability that if I have, again, so I have here A and I have here B, right? And A is, I don't know, is minus 2 and this is 5, okay? So, and the question is, for example, what is the probability that the random variable, so that we pick a point from this segment and it belongs to the to minus 2 to 0. So this has to be the integral from minus 2 to 0, right? Of the PDF, which is 1 over b minus a. So what is b minus a in this case? 7 dt, right? So it's this area from here. So this area gives me the probability that that a random variable belongs to minus 2. So from a to 0, right? So you can see that if this is greater, of course, the area is going to be greater. If this is very small, then the area is going to be very small. Now, what is the probability that in this case, what is the probability that this random variable, say psi equals 0? No. No, let's say that it belongs. So 0 is here, right? So it belongs. So 0 is between a and b, right? We have an absolutely continuous random variable, uniform, right? And I'm asking you, what is the probability that this random variable, which is continuous, is equal to 0? Zero, right? Because this is continuous. This is not discrete. Okay, so look, in the discrete case, we talk about points. In the discrete case, you can say, what is the probability that xi equals 5? That xi equals, I don't know, minus 10 or something. You can say that. And this is something, right? So if you throw a die, what is the probability that you obtain 6, right? That xi equals 6. Yeah. If you have an absolutely continuous distribution, so it means that if you have, for example, this area, and you throw a point or something, and you say, what is the probability that I will be in this point, right in this point? It's going to be 0. That's not possible, right? Because the area of the point is 0. So you can talk about what is the probability that the point is going to be from here to here. So you can ask the probability that this point is going to be in some space, in some area. That is why we have, for example, the probability that psi belongs to minus 2 to 0.
So psi is 0 because we don't know, like if we go to a certain point, it's not 0.
Okay, let me. Yeah. We can take it, but it's 0, right? Look, this is the integral from where to where? From 0 to 0. Yeah, but you have to get the idea why this is true.
Fine. Suppose we have the example that you gave. say you have like a pool of stuff and there's zero in it. So you go to a certain point and you say, at this point there's no zero. That's left. What if it is zero?
No. This is the same that we discussed previous semester, that if we have 0 and 1 here, so what is the probability that you pick 1 over 2? When we're talking about the geometric model, we say this is not possible to say, right? Because if this probability is not 0, and this is a point, so we have infinite number of points, so the probability of this is going to be infinite, right? So this can't be 0, but there are some number greater than 0. But if this is 0, then the sum of everything is going to be 0. So right. So look, the probability, if you have a continuous distribution, the probability that this is equal to something, to some given number, is 0 always. It's defined, right? Because this is just the integral from 0 to 0, and that's 0. Okay. All right. So let's take a break. What is that? It means that if x belongs to B, then this is 1. And if x doesn't belong to B, then this is 0. Right? So like, this is B, right? And the function is like this. This is 1, 1, and 0. So if x is here, then it's 1, otherwise it's 0. Indicator function. You should know this from math logic. No? Professor Dashkov. Yeah, but maybe he denoted like this. Yeah? This is the same. So, okay. So, do you have any question by now? All right. So, could you please find the CDF for that distribution? So we have the uniform distribution. We know okay, let's change this. We have it here, right? So let me erase all of this. We found this area, right? A. This area A, and we divide it by the whole area, right? Yes? Wait, but the whole area is... No, sorry. I mean, we don't find this area, but we find this length, and we divide it by B minus A. So the same that I will say here. So what is the probability that the point is between 0 and 1 over 2? That is 1 over 2 divided by 1. So the 1 is the length of the whole space, and 1 over 2 is that we care about, the thing that we're looking for. Okay. Now, so we have the PDF of the uniform distribution, right? Now let's find the CDF. Okay, so the CDF of the uniform distribution. Well, let's think about that. So let's look at the different values of x. What if x is less than a? So look, we have x being less than a, we have x being greater than b, and we have when x is between a and b, right? So if x is less than a, then we have 0, right? If x is greater than b, 1, right? Because this is the probability that we obtain a number less than b. So all these numbers. No? Okay. This is, I don't know. Again, this is here. A is 0 and b is 1. Okay, this is a and this is b. What is the probability that we obtain a number less than 0? 0, right? What is the, so, and all the possible numbers are here, right? What is the probability that we obtain a number less than 1? Okay, 1, because all the possible numbers that we can obtain are less than 1. Well, yeah, so this is for any number. So what is the probability? We have x. So x is greater than 1. So x is greater than b. So what is the probability that we have a number less or equal than 7? It's going to be 1, because all the numbers are from 0 to 1, right? Okay. Now here, what do we need to do? Again, so this is f of x, right? It's just the integral from minus infinite to x of the PDF. Yes? Yeah, exactly. So since for any value less than a, this is 0, then we can change this. This is going to be the same, that from a to x, right? And x is less or equal than b. And here we have the density, and the density is what? The density is, for any value here from a to b, is just 1 over b minus a. So this is 1 over b minus a dt. Yeah, the definition, just the definition of this. This is the definition. I mean, this is the most important thing that you should know from this semester. Okay, if you don't know this, you will fail, that's for sure. Okay, so the most important thing. Okay. Yeah, I mean, this is very important. Okay, so now what is this equal to? So this is just 1 over b minus a, and the integral of dt is t, right? From a to x. Yes, you can see, right? So here we have that this is equal to the integral from a to x of 1 over b minus a dt, and this is 1 over b minus a t from a to x. Yes, and this is what? This is so this is x minus a over b minus a, right? So here we should write x minus a over b minus a. So this is the CDF. Okay, this is the CDF for the uniform distribution, and we can easily draw this graph. So we have A here, we have B here, X, and we have here the CDF. Now, if X is less or equal than is less than A, then this is 0, right? 0. If it's greater than B, then this is 1. And between A and B, this is this line, right? So this is a line, and this line goes like this.
Wait, yeah. But yeah, like this,
In the discrete case.
So in absolute case, it breaks the rule.
No, it doesn't. No, look. So how does the CDF look like in general? No, like this. There are three properties. Non-decreasing, one, continuous from the right, and the limits. That's it. This is the main look, okay? Right? And when we have the discrete case, then we have these steps, this stairway, I don't know. But in the continuous case, we have something like this. Okay? So if, for example, you found the CDF and the graph is something like this, it means that's wrong. That's for sure wrong, okay? All right. Now, is this clear for everyone? By now, it's simple, so you should understand like most the things I've said. Good. Next. So we already know the uniform continuous distribution. Now we can talk about the normal distribution, right? The normal or Gaussian probability distribution. Okay.
You learned him in linear algebra.
In linear algebra?
Like with the matrix, like
Gauss. There are like 2 million of things named after Gauss. So, yeah. So before this, do you know what is the Gauss? Or I think maybe you did you know this like the Poisson integral. So let's say how much you remember from calculus. No? So what is the integral from minus infinite to plus infinite of e to the minus x squared dx? This is 1. Oh, sorry, this is the square root of pi. Okay? So you can prove this from calculus. So this is the, so because of this, this is we call this the Gaussian integral, right? Because of this, you will see why. So we need only to pick this thing to here, and we will get that this integral is 1, right? So we get an integral from minus infinite to plus infinite, which give us 1. Then of course we obtain some density, right? Let me show you that. So what is the normal distribution? So we denote it like this. A and sigma squared. So a normal distribution has 2 parameters, A and sigma squared. And later we will see that A is just the expected value of this random variable, and sigma squared is just the variance. Okay. Now, in this case we have that x is just the set of the real numbers, right? So all the possible values that it can take, it just hold all the real numbers. And for every real number, we have that the PDF is like this: 1 over the square root of 2 pi sigma squared e to the minus x minus a squared over 2 times sigma squared. So this is the PDF of the normal distribution. Okay, how does it look like? Well, this is the famous bell-shaped curve like this. So every time that you hear you know something about you hear something about probability distribution, you will think about something like this. This is because this is the normal distribution. This is the most famous distribution, and this is very important because we will prove at the end I mean in 2 months, that every possible distribution that we know, right? Every possible, it doesn't matter if it's discrete, continuous, or so on, it converges to the normal distribution, right? So we don't need anymore, we won't need anymore these distributions because all of them converges to this distribution. So this is the most important distribution, okay? And this is the PDF of this distribution, okay? What do we have here? So in this case, so here is A. So A, so this function, what do you need to know about this function? This function is even, right? So what does it mean that a function is even? We have odd functions and even functions. I think in English it's the same. Huh? Yes, exactly. So it means that if you have like a mirror here, so it's exactly the same, right? Yes. So here in the middle, right in the middle, we have A. This A from here. That is why this is the expected value, right? And how the form of this curve, this somehow this means this is sigma squared. So how far it goes from the center, okay? And where is A? Well, that's so. For example, if we have some A here, then it will be here, right? If we change this sigma square, then it can be like this, and so on, right? So we can change these two parameters, and we will obtain all the possible values. So this distribution is actually a family of distributions, because we have, for all the possible values of A and sigma, we have infinite possible distributions. Okay, good. So we have that. Great. Now, and using this integral, you can show you can be sure that the integral of from minus infinite to plus infinite of this is going to be 1. Okay, so that is why this is important to know. This integral is important to know. Now, what about the CDF? The CDF is, first, we don't need it. Okay, so but the CDF, for the CDF, we just have to write this. Okay, so there's something complex with some really complicated that I don't even remember. So we don't need the CDF. Of course, the CDF is defined and so on, but we only are going to work with the PDF. Okay, this is the PDF. Good. What else do?
Let's say
Yes.
probabilities like binomials, I can think of, we take a point and flip it 10 times.
Mm-hmm.
So I can imagine binomial distribution. I can imagine the CDF type.
Yeah, look, the most like common example is if you look at the height of people, right? So if you look at all the people in the world, and you so from, I don't know, from 0 to 2 meters, 2.5 meters, right? Maybe somebody, right? And I don't know, the middle is 1.8, 1.7, I don't know, right? So here is the height of the people, right? And here is the number of persons with this height. So the graph that you will get is something like this. So you will get the Gauss bell, right? So the distribution, so if you say the random variable is the height of the people, you will get that this random variable has a normal distribution. Because there's a lot of people here with this height, and there's there are not too many people with, I don't know, here, that are higher than 2 meters or something, right? So this is like example of that. And in the nature, in this real world, most of the things work like this. There's a lot of something. Yeah, all of that. So the normal distribution is everywhere. Okay. Good. Great. So what else do we need? Check. Yeah. So we are not going to write the CDF, but we can somehow draw the CDF. So this is one, and of course it's going to be something like this, right? Continuous. But in point A, what should I write here? You can tell me. So I mean, do you get the idea? Just so this is X, this is the CDF, right? So what is f of A? Yeah, so we have to use the formula. So f of A is just the integral from minus infinite to A of all of this, right? So 1 over square root of 2 pi sigma squared e to the minus 0. So we have here 0, x minus A, 0. So this is just but actually we don't need to do that, sorry. All that we need is to look at this. And I told you that this function is even. So the just a second. So f of A is the probability that the random variable is between minus infinity and A. So it's all this area. Well, this is equal to what? This area. The person who told me is get 0.5 in the final.
They taking both of the full area divided by 2.
Yeah. So
Can you repeat the question, sir?
what is the area? Oh, under this line here, from minus infinity to A.
With the integration from A to 0.
No. So who can tell me? 0.5 points in your final grade. Which final point? This is A, sorry. So this is A. A can be 0, of course. Huh? No. We are looking at this. So what should I write here? Huh? Yes. Yes. And this is symmetric. Okay, you have 0.5. Let me write that. Oh, I forgot. Okay, wait. You are Ashish, right? Now, is this clear for everyone? Why this is 1 over 2? Yes? So here we have 1/2. Okay? Good. Great. Now, let's move forward. So we have the next example is the exponential distribution. So this is example number 3. The exponential distribution with parameter lambda. And lambda is greater than 0. So there are many different examples of distributions, okay? But the main distributions are, let me write here. So we have the uniform, we have the normal distribution, and we have the gamma distribution. Sorry, gamma distribution. From the gamma distribution, there are many different special cases of the gamma distribution. And here we have the exponential distribution. We also have here, how's the name? The Cauchy distribution. In English, I think it's like this, Cauchy, right? No? It's the first time I write in English. The Cauchy distribution, and there's a lot of distributions, and they are just in a special case of the gamma distribution. But the gamma distribution is too difficult, so we are going to look just to the two special cases, the exponential distribution and the Cauchy distribution. Okay? Because the gamma distribution uses the gamma function and so on, and the zeta function, and we are not going to use that. Yeah. So do you know what a gamma function is? Well, you should know it. No, I think, no? From calculus. No, the gamma function of a number, no? Okay. So look, the exponential distribution with parameter lambda. First, well, what you should know. So when do we use this, right? So like in life, this is for modeling time. So how many time, for example, this is some example that I listened about. So it's how many how's the name of that? I forgot. How many people you need in McDonald's, like selling people, right? Just that everyone have to wait no more than, I don't know, 2 minutes on the line or something like that. So if you want to solve this, so here the random variable is the time that you have to wait, right? And here, so this random variable, this distribution give us the description of the time, okay? So that is why this random variable is always greater than 0, right? Since we're talking about time, okay? So look, if x is less than 0, then the density is 0. Okay, so it means that if this is the density, so this is 0. Okay, here we have 0. And in general, then the density is going to be lambda e to the minus lambda x. And here we write for every x greater or equal than 0. So this is just writing like if x is greater or equal than 0. So this function is something like this. So here we have lambda, right? If x is 0, then this is 1, so we have lambda. And this goes like this. Yeah. Yes. Lambda is some parameter, right? In the same that we had, for example, for the Poisson distribution, We have the Poisson distribution with parameter lambda also, right? So some parameters that we give. And the CDF is, I think, 1 minus e to the minus lambda x. If I'm not mistaken. Yeah, let me check. It's okay. And the CDF looks like this. So this is the CDF. So we have 0, right? And then we have something like this. Up to 1, right? So infinitely goes to 1. Right. Good. And so this is the exponential distribution. And finally, we can talk about the Cauchy distribution. But I just don't remember how it looks like. So let's talk about the Cauchy distribution later because I don't remember. Okay, so and that's it. So these are the main distributions that we need by now. Okay, so by now, do you have any question? Everything is clear. Perfect. Okay, so let's do the following. So now let's define finally what a random variable is. So we've been talking about distributions, but so for example, question: what is a distribution?
How the elements are distributed, like suppose.
No, don't think about the word distribution. Think about the definition of a distribution. I don't need to hear that in the exam. So what is a distribution, a probability distribution?
The probability distribution are a way that the certain values and certain outcomes are spaced out.
What is a probability distribution? I've been talking about probability distribution for 2 lectures.
We're very good students.
So what is a probability distribution, right? So where is this probability distribution coming from, right? Again, the same, F. So what is a probability? So this is, we call this a probability measure, right? So if we have a probability measure on this space, on this probability space, this is called a probability distribution. Okay?
The same probability measure, but
in this space, in the measurable space formed by the real numbers and the Borel sigma algebra. So in the exam, what is a probability distribution? A probability distribution is any probability measure defined of the probability space on the measurable space formed by the real numbers and the Borel sigma algebra. A probability distribution is any probability measure defined of the measurable space defined by the real numbers and the Borel sigma algebra. Okay, so this is the answer. Now, do you understand everything that I said? No, you didn't, right? So what part do you understand? I mean, I need you to understand this very good. Borel sigma algebra. Is that clear? No? Okay, so just let me think. So again, so look, keywords. Let's say keywords. Probability space. Probability space. What is a probability space? No. A probability space is this. Is some space defined by these three objects. When we have any set, the sigma algebra defined on this set and some probability measure. This is a probability space. Now, what is a measurable space? A measurable space, a measurable space, yes. Instead of taking this, we take only these two. So it's any set and a sigma algebra defined on this set. This is a measurable space. And a space which we can measure because we have a sigma algebra on it. So what is a probability distribution? Right. So there is not the probability distribution. There are many probability distributions. For example, what? Give me one example of a probability distribution. Huh? The normal distribution, the Poisson distribution, the binomial distribution, all of these are distributions, are functions. Functions, right? Functions from the Borel sigma algebra to 0 and 1. So any such function from the Borel sigma algebra to 0 and 1 is a probability distribution. Any such function, and of course this function is not unique. I already gave you many examples. The Cauchy distribution, the normal distribution, all of these distributions are functions, are probability measures, are probability distributions. Okay? And look, we haven't talked about random variables by now, right? So if we want to define a probability distribution, we don't need to talk about a random variable. We did that previous semester, but now we don't have to do that because actually the probability distribution are before. Okay. Now, if we want to define a random variable, we need the definition of a probability distribution, right? So look. Perfect. So we have two different measurable spaces. This one, any one, so omega is any set. The set of cars, the set of persons, the set of anything you want. And this is another set, measurable. This is the set of the real numbers and the Borel sigma algebra on it. So we take the set of the real numbers and take all the possible open sets and closed intervals and so on, right? So B is, for example, this. And F, in this case, this is F, right? This is the sigma algebra on F, on this omega. So we have a set in a sigma algebra, and here we have a set in a sigma algebra, right? Two different probability spaces. Two different probability spaces. Now we can define a function from here to here. Let's call it psi. So we have some function from this probability space to this probability space. Yes. And if here we had this probability measure, right? Then here we will get this probability measure is going to be defined over here, and it's defined by this random variable psi. So this probability measure, this is the probability distribution, the probability measure, let's say, probability measure, generated by psi. And this is a probability distribution. This is not. This is. Okay? And to finish with this, so the definition of a probability of a random variable, psi is a random variable if this is a function from omega, right, to the set of the real numbers such that this function is measurable. And we already know that the function is measurable if such that the preimage, so if we have this psi minus 1, so the preimage of any b, so here this is the preimage of any b, so such that c for any just such that for any b, so for any b from here, the preimage so the preimage is going to be some set, right? So this set from here has to be an element of F. So this preimage has to be an event, so an element of F. Well, yeah, because this is a function, right? Yeah. So a random variable is a function, just like this is calculus, I would say. But and that's it. So this is the definition of a random variable. And yeah, that's it for the lecture.